So what I did in here was I just went ahead and put our graph back up. It's a little nicer looking because I used, some other tools. But now that we have a graph, the rest of this should go, I think, fairly quickly. And we maybe already did the first one, didn't we? Okay, perfect. Courtney's shaking her head, yes. So the first question said, now that we have our piecewise function, what is the limit as x approaches 0? So we did this yesterday. We said, here's x equals 0. Go on either side, like maybe -1 and 1, and start walking along the path. And we get back to a y value of -2. So we did that one yesterday. Perfect. Let's take a look at the second question. And some of you may have already done this. That's okay. The limit as x approaches 2. And again, it doesn't say from the left or from the right, so it means both. So as x approaches 2, so here's x equals 2. I'm going to put my hands on either side. I'm going to go find the graph on either side. And we start walking along, walking along, walking along. Do my fingers go to the same place? No, not even close. So what do we say about the limit? Does not exist. Remember, for a limit to exist, we need to approach the same location, and we're not. We have a pretty big gap there. Okay. Good. Now I know this is hard to see, so you don't want to look at your paper. The next one says, what's the limit as x approaches 2 from the right? Great review question. That just means you're just going to use your right hand instead of both hands. Still x equals 2, so we start on the right side, we start walking in. As I get closer and closer and closer to 2, where does my finger end up? At 1. And then the fourth question says, what is the limit as x approaches positive infinity? And I didn't put this on here. We know we have a line off to the right. We had a line going off to the left. As x approaches infinity, infinity is a huge number. My graph paper is only going out to like 6.4. That's not very big. So we have to think about what is this graph doing as it goes off the page. Look at that right end. As this graph continues on forever, where's my pen going to go? On. It's going to go on forever. It's going to go up forever, isn't it? What is the y value getting close to as I go off the paper? Infinity. I should switch colors. I need to keep that in mind. Okay. Remember, a limit to infinity is saying, what is the end doing? Where is the end going? Is it going up? Is it going down? Or is it flattening out? Okay. Awesome. Here's a great question. I love this review. Does this graph have any discontinuities? What does that mean for a graph to be discontinuous? We've talked about continuity. It's been a while. Let me rephrase. What would it mean if, and this can be from anyone at home as well. What does it mean if a graph is continuous? It goes on forever. What else could we say? It's not wrong. Let's say I don't run on treadmills. I hate running on treadmills. But let's say I said I was running on a treadmill continuously for 30 minutes. What does that tell you? I didn't stop. Yeah, I didn't stop. I didn't take a break. Agreed? There's no break in what I was doing. When we translate that into the idea of graphing, same idea. Can you graph this picture without stopping? Can you graph this without picking up your pencil? Remember we used that phrase this year? It was a long time ago. So when we talk about a graph being continuous, we're asking, can you draw it without picking up your pencil? This is a piecewise. It had 3 pieces. Can I draw it as a whole graph without picking up my pencil? I don't think so, right? Because I can start, I would start way down here and I'd start and I have to pick up my pencil to jump, physically to jump up to that 3rd piece. So does the graph have any discontinuities? The answer is yes, because it is not continuous. It is not continuous. Whoops. Oh, switch colors on me. At x equals 2. So what I love here is it's just kind of bringing us back to some ideas that we've already talked about this year. There's a break in the graph. In fact, we call it a jump. That's a very technical math term. We call it a jump in the graph. You have to pick up your pencil and jump to the next spot. Okay. All right. So everything in here was all review. It's just kind of nice to tie some old stuff together. Okay. All right. Let's take a look at this next one. Sketch the graph of a function. And first of all, I'm going to say a function. It doesn't say the function. Sketch the graph of a function, meaning there's probably more than one answer, whose domain is all real numbers. I'm going to stop there for a second. Two key words. The first one is a function. And we know if the graph is going to be a function, it has to pass the vertical line test. So I'm just going to jot that down. Pass the vertical line test. VLT, vertical line, I just made that abbreviation up. Whose domain is all real numbers. First of all, what is domain? It's all the x values, right? The domain says which x values are you going to use. So if they're saying the domain is all real numbers, they're telling us to use all of them. Use all of the x values. So there should be no vertical asymptotes. There should be no gaps in the graph horizontally. We want to use all of them. All right. Now let's get to the meat here where it says such that, I should use a highlighter, the limit as x approaches -2 from the right does not equal the limit as x approaches -2 from the left. Okay, so they're talking about x equals -2. So something funky maybe is happening at x equals -2. Maybe I'll just put a little mark down there. What does it mean if the limit coming in from the left does not equal the limit coming in from the right? You can use very informal words here. We don't have to use math terms. Think about what my hands would be doing.
You would have to jump.
You'd have to jump, right? Remember, the limit coming in from the left is my left hand. That's to your perspective. The limit coming in from the right is my right hand. If they're not equal, that means there should be some sort of gap there, right? It basically is saying, don't come to the same place. You go your way, I'll go mine, right? So your graph can look different than mine as long as we come in from the left and go to one destination, and we come in from the right and we go to another destination. Other than that, I don't care what the shape is. You could have two lines there. You could get crazy and draw some curves. I'd be careful trying to get too crazy because then we may not pass the vertical line test. So I'm trying to keep it pretty simple. The shape of these two pieces doesn't matter. What matters is that at -2, they do not go to the same place. So maybe I'll put an end on each, an arrow on each end to say it goes on forever. So far, my graph passes the vertical line test, right? I can draw a vertical line and it's not like I have something over here where I'm like, ooh, that's a problem, right? I don't have that, so get rid of those. Let me ask this question. For right now, I just have open circles there. Can I fill them in?
Only one. Right?
Only one. Because if I fill them both in, then it doesn't pass the vertical line test. I'm not a function, so we can't fill them both in. Do I have to fill one in? Or can I leave them both open? Katie's saying we can leave them both open. We can't fill them both in. I agree with that. Can I leave them both open?
No.
No. Why not? Because they said the domain is all real numbers. And if I leave them both open, then I'm telling them we never used x equals -2, but they're saying you have to. You have to use every x. So this is where it's a case where you have to fill in exactly one of those circles. You cannot fill them both in or it's not a function. And you cannot leave them both open because then we're implying that we're not using x equals -2. There's a lot going on in there. graphing it was not hard, but thinking through all of those seemingly at first simple things they were saying, trying to think that through, makes us really have to go back and talk about domain and what that means. Other than that, your graph could look different than mine, like I said, but the big deal is we need to have some sort of jump in the graph, and we have to have one of those filled in and one of them left open. That's what we have to have the same. Okay? Good. All right. We have one more slide, I think, don't we? Well, we have two more, but I think one was just kind of some extra practice problems. Let's finish up with this one. It even says review. This is old review, taking us back to, gosh, I don't even know when, unit 2 maybe. If f of x equals negative 2 over 1 plus x, find and simplify f of radical 3. Jalen, what are they asking us to do here?
Simplify.
We will simplify, but the question is what? What are we going to simplify? What are we going to do first? Let me rephrase my question. How do we find f of radical 3? What is that telling us to do?
1/3.
Well, let's go back here. It's kind of like the homework question that Andrew asked about today. F of blank equals negative 2 over 1 plus blank. Function notation, right? All I did was take out the x's and I just left a blank spot there, right? They're saying find f of radical 3, so they put a radical 3 in here. So I should also put a radical 3 down here, shouldn't I? If they said find f of 0, we'd go plug in a 0. If they said find f of 2, we'd go plug in a 2. They just said find f of radical 3. That means go plug in a radical 3. They're giving us an x value and they're asking us to find a y. That's what function notation is. We found it, right? We said, there it is. Let's not simplify because it says find and simplify. Why is this not simple right here? There's a radical in the bottom. So maybe we should just rewrite this. We have negative 2 because we don't need the parentheses anymore. Don't let those bother you. We don't need them there. And Andrew says there's a radical in the bottom. So the question is, how do we get rid of a radical in the bottom? This can go for anyone. How do we fix this? Even those of you at home can answer this question for us. Perfect. Andrew's remembering that if you want to, first of all, we have a binomial down here, and I'm going to repeat what Andrew said. Down here we have 1 plus radical 3, and he's remembering that if you want to eliminate a radical in a binomial, you need to multiply by, in this case, 1 minus radical 3 on the top and bottom. Does anyone remember the word we called that? Starts with the letter C. Called the conjugate. Not that that matters. We are going to multiply by the conjugate. That's how we eliminate radicals in a denominator when we have binomials. Now, I've not left myself a whole lot of room, so this is just me. I'm going to rewrite it. So I have negative 2 times the quantity 1 minus radical 3. That's on the top. And on the bottom, I have 1 plus radical 3 times 1 minus radical 3. This is just me saying, hey, if we're going to multiply fractions, just multiply straight across the top, straight across the bottom. The bottom is what's been my concern. I could certainly distribute that too, but I'm going to hold off on distributing the 2, and I think we'll see why in a minute. The bottom is what's causing the problem. Let's focus on the bottom. Remember, a conjugate is setting us up for a difference of squares. So it should be easy for us to FOIL this, because when it's a difference of squares, you don't need to do all 4 pieces. We're going to have the first 1 times 1 is 1. When you go to the outside, you get a negative radical 3. And when you go to the inside, you get a positive radical 3. So those are gone. That's how that difference of squares works. So let's not even write those down. And then we go to the last pieces. We have a positive radical 3 times a negative radical 3. Oh, positive times a negative is a negative. Radical 3 times radical 3 is 3. The radical is gone. That's supposed to happen. If it didn't, that means we did something wrong. So again, I'm not going to distribute the top because I'm maybe thinking we can reduce this. That's how we reduce fractions. We leave them factored. Oh my gosh, it's perfect, isn't it? I have a -2 divided by a -2. I'm glad I didn't distribute that -2 because then I would have ended up factoring it back out. And we're left with 1 minus radical 3. I brought this back up as a review for a reason. On Friday this week, we're going to go back and we're going to do some work with imaginary numbers. Woo! And imaginary numbers are really radicals. So I just thought maybe now would be a great time to start kind of doing that little review. Okay? Okay. Awesome. So here's what I'm going to do. I'm going to stop this recording because we're not going to finish anything else. So we have a couple